Hey everybody, Dr. A here, and in this video we're going to be exploring an example of computing the centroid of an area using the integral formulation. So before we jump into it, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's get started. In this example, we're being asked to compute the location of the centroid of the area bounded by the linear segment. So in this graph here, in this plot, this is the linear segment we're interested in, okay? Linear segment, straight line. The area that we're trying to find the centroid of is this shaded area here, okay? So we notice that if this is a linear segment, then this is forming a triangle. And more specifically, this is forming a right triangle with a base dimension of b, we see that here, and a height of h, all right? So let's go ahead and figure out how we're going to tackle this problem. The first thing we need to notice under our solution is that this is a 2D area problem. So because of that, we're going to have an x-coordinate and a y-coordinate for the centroid, and we need to use the area version of our centroid formulations. So we're going to say x bar is going to be the integral of x tilde dA divided by dA, and then, of course, y bar is going to be equal to the integral y tilde dA divided by, oh, forgot my integral symbol, divided by integral dA. Okay, so this is, again, just the area version of the centroid integral formulas. Nothing mind-blowing yet, okay? So the next thing we need to do is notice that we were not given an equation, and we're using the integral form, so we need some kind of equation of this line. So let's make a note of that. We're going to say, we need an equation of the line to compute integrals, okay? So if you look at this, you may even be able to just look at this and tell me what this equation is. If you can, that's awesome. If not, I'm going to tell you how to do it, but it really is just an Algebra 1 concept. If you have a line passing through the origin and you know 2 points on that line, we know this point up here is b comma h, and we know that the origin is 0 comma 0, then we can clearly say that the slope of this line is equal to h over b, right? It's rise over run, and this is an increasing line, okay? And so that's the slope of the line. And if it's passing through the origin, then we know that its y-intercept is 0. So the equation for the line is simply y equals h over b times x, where, again, h over b is the slope, and then x is the independent variable. So now we know the equation of the line, no problem, all right? So now we got something that we can eventually take the integral of. So let's tackle x bar first. All right? So let's say compute x bar. So in order to do that, I'm going to help us visualize this a little bit better with redrawing this line, okay? So we have B right here, and of course we have H right here, and we know that this is our area that we're interested in, okay? And again, we figured out that y equals h over bx. All right, so the first thing we need to try to figure out is what is dA, all right? So here's what I'm going to do. I'm going to look at this little area slice right here, and I'm going to say that is dA. And we're going to say that this area slice has a width of dx, okay? So this is an infinitesimal slice of area, all right? Now, we also need the height, right? So again, we need to get dA. So it's going to be, if this is a little infinitesimal rectangle, we need dx times whatever this height is. Well, if you just look at it, the height of a rectangle here, even if we drew the rectangle over here, okay, the height of that rectangle is equal to just the function itself, right? So that's going to be y dx. Well, we know what y is. Y is given, we figured out y, the equation for y. So we're going to say dA is equal to h over b times x dx. And there you go. There's our dA. So the dA that we're going to use in our formulation, we got it now. And in fact, even though we're doing this for x bar first, that's the same dA that we can use for y bar as well. So I can check those off. Let's look at x tilde now. That's where we got to put our thinking caps on a little bit more. So x tilde. So x tilde is, again, it's the moment arm. Let's change colors, make it green. X tilde is the moment arm from the y-axis to the centroid of x tilde to the centroid of a slice dA. All right. So again, x tilde is a moment arm from y-axis to centroid of dA. Okay. So if that is x tilde, then what's a kind of a formulation we can look at to figure out what x tilde is? Well, if you look at this, the centroid of that slice dA, the x coordinate of it, x tilde, will correspond with what? Well, it just corresponds with an x value right on the curve, right? Or right on the line. All right. So if that's the case and it's always measured from y, then x tilde for this situation is just going to be equal to the variable x. Because again, all we're doing is we're going from our y-axis to the curve or to the line itself. So that's a distance x right here. All right. So here we go. We're ready to get started with x bar. We're going to say x bar equals the integral, and since we are using dx as our differential, we're integrating with respect to x. We're going to integrate from where to where? 0 to b. Okay, so we're going to go 0 to b. X tilde is x, and then dA is h over bx dx, and then the denominator is integral 0 to b of just dA, which is h over bx dx. Okay, so this is pretty simple. We really don't have any numbers here, so we need to do this kind of in our heads, but it's simple enough, right? So that they're both, polynomials. So that numerator becomes x cubed over 3 times h over b, of course, evaluated from 0 to b. And then the denominator becomes x squared over 2 times h over b, evaluated from 0 to b. So now that we've evaluated the integrals, we can see some convenient cancellations. We have an h over b and an h over b that are just constants, so those cancel. And really what's important that we don't cancel anything just yet is the variables, because we have to substitute in these integration limits. So we're going to end up with b cubed over 3 multiplied by 2 over b squared. And again, I just skipped an algebra step here, but you maybe want to work out some steps in between here so you can see it more clearly. But I get x bar is equal to 2b over 3, okay? And so where is that going to, that's 2/3 of b, so I'm going to say my x bar value is about somewhere right here, right? X bar is 2/3 of b, okay? Now, what about y bar? So we're done with x bar, there you go. What about y bar? Let's say, come down here, we're going to say compute y bar, all right? So I'm going to redraw this. Now, I really suggest when you're doing these problems, redraw them as many times as you need, okay? That's how you're going to learn it. The whole objective is to learn it and then apply it in maybe later classes, okay? So here's h right here, and again, I'm just redrawing my original figure. and this is y equals h over bx. So now I'm looking for y bar, okay? I'm looking for y bar. So I can still look at a same little differential area slice, dA, and dA is, this is dx, and then the height here is y, so same as before, y dx, and so dA is still my h over bx and then dx, okay? So that part's the same. What's different is y bar, okay? Y bar. What is y bar in my case here, okay? So y bar, not y bar, I'm sorry, y tilde, y tilde. So what is y tilde in my situation here? So again, y tilde is going to be the moment arm right here, y tilde. Y tilde equals moment arm from centroid of dA, that's just the middle of dA, the middle of that little slice, to the x-axis. So what is y bar in this particular case? Well, let's think about it. dA right here is measured from the x-axis up to the function, right? This thing is dA, right? So dA is, the height of dA is always y. Well, if you're looking at this little bitty slice, what do you think y bar is going to be if y bar is going to the mid-height of y? Think about that. I'm about to tell you. If that's the case, I keep saying y bar, I mean y tilde, I'm sorry. Y tilde is equal to y over 2, okay? Y tilde is y over 2. Again, y tilde is going from the x-axis to the center or the centroid of the slice dA. And if dA has a height of y, then y tilde has to be a height of y over 2. So there's my y tilde. So now I'm ready to calculate my y bar as integral. And we're still integrating with respect to dx, right? We're still integrating with respect to dx. So we're integrating from 0 to b still, okay? So that's where we got to be mathematically proper. You know, I say to you guys all the time, be mathematically proper, be mathematically proper. This is one of these topics that you'll really mess up if you're not being mathematically proper and keeping track of things. You're integrating with respect to a variable dx, so you got to go from 0 to b, which b is along the x-axis, okay? And so then we have y over 2 and y dx divided by the integral of b, and then that's the integral, of course, is dA, so it's y dx, and we know the function for y, so integral from 0 to b of h over 2b times x times h over bx dx, and then this denominator is the same as what it was for x bar, h over bx dx. And let's go ahead and punch this through. Y bar equals, and we got a lot of constants here that we can kind of gather up. So we would have h squared over 2b squared, and then x cubed over 3. And that's, of course, evaluated from 0 to b. And then the denominator is h over b times x squared over 2, evaluated from 0 to b. So we can cancel some things. We can cancel this h over b with one of these h's and one of these b's. And then we're going to have h over 2b times b cubed over 3 divided by b squared over 2. And doing a little bit of rearranging, got a lot of fractions here. H over 2b times b cubed over 3 times 2 over b squared. So let's see how we can simplify things and just do an algebra at this point. We can cancel this b squared with 2 of these, and then this b squared cancels with the last b here. This 2 cancels with this 2, and then we are left with h over 3, okay? And so my y bar is going to be somewhere about right here at h over 3. Okay, so if I want to make a final sketch of this, just to make sure we can visualize things okay. There's B, there's H. Y bar is about right here. And then X bar is about right here. X bar was 2/3 of B, and Y bar is H over 3. So there's my centroid, okay? And so here's an interesting thing to note, all right? We're gonna make a note here. Note that the centroid of all triangles is 1/3 of the dimension from the quote flat side and 2/3 of the dimension of the point in both directions, okay? So if we take a look at this, we say X bar is 2/3 of B from the point of the triangle. And so that would mean it's 1/3 back here. Like if you wanted to, populate this dimension line, this would be B over 3 because it's 1/3 of the dimension from the flat side, right? And then in the other direction, same kind of thing. If you look at Y bar, it's H over 3 from the flat side in the Y direction, or it would be 2/3 of H from the point up here.